the number of carbon atoms, the prefix. I said up to here is the only place where you have to worry about differences. After that, the number is stays the same, or 6, 7, 8, 9, 10. There are some different isomers. First of all, are these isomers? These are all saturated. Notice that there's 4 bonds to this carbon, 4 bonds to this, 4 bonds to this. These are all saturated. They're all alkanes. How would you tell if they're the same, if they're isomers? Count the carbons and the hydrogens, right? So here I see 1, 2, 3, 4, 5, 6, 7, C7. 3, 4, 6, 8, 10, 11, 14. Now we do the same thing over here. 1, 2, 3, 4, 5, 6, 7, C7. 3, 4, 7, 8, 10, 12, 14. They both have the same number of carbons and hydrogens. They're isomers. What about the nomenclature? Wow. Fortunately, well, this one I might ask you. Now, one of the first things you'll notice when I was talking about alkanes, I wrote this formula. C2H2O plus 2. But this is what? The formula for an alkene. Well, these were saturated. Alkenes had the double bond. Meaning you got rid of a pair of hydrogens. There could be other things on here. But that looks like an alkene. But there's no double bond. It's still a saturated molecule, so it is an alkane because there are no double bonds. That means this is a cyclic structure. Oops, I can't spell cyclic. So there's a 5-carbon chain, pentane. And now we have methyl substituents. Okay? So this is cyclopentane, and it's dimethyl. By the way, when you do this, sometimes you have to plan this ahead so you don't have weird looking spaces in your name. And now we can say 1, 2, 3. So it's 1, 3. Or we count the other way, 1, 2, 3. Like that. Now when you have a di, unless it's the unique case like we had the dimethyl propane, where there's only one place we could put them, you always have to have 2 numbers for di, 3 numbers for 3, locating where the different substituents are. Separate numbers with commas, words and numbers with hyphens or dashes. This one we could name, except we call this isopropyl or something, and we're not going to get that far into the nomenclature, so we're not going to worry about it. But this would be essentially a cyclobutane with this fancy substituent on it, which is more complex than we want to do for substituents. Okay. So now we're introducing what is known as functional isomers. Notice this one has the same formula as the alkenes. The alkenes ended in ENE. This ends in ANE. Types of isomers that I discussed again. In other words, we had different numerical prefixes. We saw the butane, the propane, and the pentane over there with different constituents. So we had different, the numerical prefix was different. as I said, the functional groups determine the word ending for the name, so you'll see different word endings. Oops, I got my indentation wrong because I'm doing different types of isomers, so I'm going to put that. Okay. So far we've seen two different types of isomerism. They're all based on differences in structure, so you can't just say they're you can call them in general structural isomers, but sometimes I want to be a little more specific than that. Okay. So again, when we're doing alkanes or alkenes, we're looking for the longest carbon chain. Notice this isn't an alkene because of this word ending. Longest carbon chain with the double bond. And you number the chain so that the first carbon of the double bond has the lower of two possibilities. In other words, you can either number left to right or right to left, and it has to have the lower of two possibilities. Now, one of the things I didn't mention over there, when we do inorganic chemistry, the things we were doing at the beginning of the semester, they talk about 400,000 to 500,000 compounds. When they talk about organic chemistry, they talk about 5 to 6 million compounds, and it keeps getting bigger every year. And that's because of the existence of all of these isomers. I found an old slide somewhere. He was just talking about isomers. And notice if you talk about one isomer, that doesn't make sense. He's doing as you have the number of carbons increase, there's only one molecule you can draw when N is 1, but when it's 4, you can draw 2, 5. And then notice we have 20 carbons, 366,000 isomers. And he says do N is equal to 40. And you take the rest of your life to do that because there's 62 billion isomers or something. Okay, there's no simple formula for calculating how many isomers, but that's one of the problems with organic chemistry. That's why there's so many compounds, because there's different ways of putting these things together. So we're working with relatively small molecules, because I don't want to count carbons, as I said. But as you add more and more carbons in there, the number of isomer possibilities go up, and as you start tossing in some other functional groups, it increases even more. So I thought that was interesting. Yes, that's probably isomers of C2H, C4H82, and we wouldn't put long enough to do it. Okay, here's an alkane. How would you name that one? Well, what? first things you do is look for the longest carbon chain. Like 7, 7, 1, 2, 3, 4, 5, 6. That didn't work. So 1, 2, 3, 4, 5, 6, 7. But look at this. If I go 1, 2, 3, 4, 5, 6, 7, 8. 8 is the longest carbon chain. Okay. So that's an octane. Here are methyl groups. What's this one? 2 carbons, that's an ethyl group. So you have tongue twisters when you do organic chemistry, you call it ethyl methyl or things like that. But let's do it correctly. Now, whoops. If I start numbering from here, it's 1, 2, 3, 4. There's something on the 4. And 5, 6. There's something on the 6. If I start up there, so this is 4, 6, 6. That adds up to what? 4, 6, 6 is 14. If I go this way, 1, 2. It's 1, 2. This is 3, 3. 4, 5. 3, 3, 5 adds up to 11. So we start numbering from up there because you want the lower set of numbers. So it would be 3, 3 dimethyl. Now the other thing is when you start having more substituents, they're alphabetized. So this is M. The other one was ethyl over here. So ethyl would come first because of that. In the old days it used to be based on complexity. Then methyl would come first and ethyl would come second, but now everything's done by alphabet. Because the computer, you have to do extra programming steps for it to decide which is a more complex thing. So it can always do alphabet really well. You don't use the numerical prefixes. Now what did I count here? I counted 1, 2, 3, 4, 5. So it's 5 ethyl. Notice the hyphens between words and numbers, commas between numbers. And finally, we counted 8 carbons. It's all saturated, so it's octane. Questions? Then we got to the double bonds. And as I said, notice that I erased it before you draw it. That's what Easy Ed always did. By the time you looked up there the second time, it was gone. In fact, he had filled the board twice already. Okay, so coming back to this thing, you want the longest carbon chain. So here's F. Now, if you notice, after that, it said in parentheses, ethylene. This is the IUPAC name. That's the only kind of name I want you to give me. But this is what is called the common name for that molecule. So it's also referred to as ethylene. Coming on your organic chemistry instructor, they may use a lot of common names. Other people will stick, hopefully, to the IUPAC name. Okay? Propene. Okay. And there's not much you can do with that. But here's so now I've moved the double bond around. This is called 1-propene. Propene. So now we have examples of the so-called positional isomer. where you're moving things around. If I look at this thing. I move the methyl group from the number 2 carbon to the number 3 carbon. And by the way, you would never call it something like 4-methyl. The other one, it doesn't matter which way you count, it comes out to be 3. But you always want the lower set of numbers for your substituents. Yes?
So even though there's 4 carbons and...
I didn't finish it.
Okay.
What's next? What do I have to do to finish it? That's not a next, that's a y. I have to finish the molecule. 1, 2, 3, 4, 5. Is that what your question was, or?
It's more about the propane. Because I see the 3 carbons is propane and 4.
Oh, I can't count. This is propene, it's 3, this is what? So you gotta watch that all the time. Okay. So the next thing we have, these are called positional isomers, where the only thing that changes is the number of locating substituents or functional groups. One of the things is, if you name it correctly, you can distinguish it, you can determine whether you have an isomer or not. For instance, if you name this correctly, it's still 2-methylpentane, so it's the same name, so it's not an isomer, it's just the molecule drawn backwards. Yes?
Okay, so I understand that the butene, the line is because it's on the double bond on the 1 carbon, butene is because the double bond's on the 2 carbon. But I don't understand the 2 and the 3 on the methyl pentane.
Okay, well, you have to number the longest carbon chain, right?
Right.
So if I go 1, 2, 3, it's located on the 3rd carbon. If I go 1, 2, 3, it's still located on the 3rd carbon. It doesn't matter which way I number it.
But the one above it does.
This I can, yeah, because it always has to have the lower. So this is 1, 2 methyl. This one is 1, 2, because I numbered from the other direction.
Okay. It's just whatever direction is the lowest.
Right.
Okay.
That's the key. You always want the lower set. In other words, there's only 2 possible ways of numbering, counting from one end of the molecule to the other, or in the reverse direction, whichever gives you the lower set of numbers for the substituent locating numbers. That's the correct way of numbering it. Now this functional group determines this, because if I have something like this, it's still a 1-butene, but now it's 1, 2, 3 methyl 1-butene. And by the way, the more modern way, Dr. Jones informs me because he doesn't like the way I do it. Is but-2-ene or butene or whatever you want to call it. He didn't tell me how to pronounce it, he just said that's what you're supposed to write. Okay. So that's the new and modern way of doing it. That's because you're starting to put a lot more junk in the molecules, or the molecules they're working with have more and more substituents, so you have more and more numbers floating around. So the number that locates where the functional group is before you get to the functional group. And it makes sense to me. But most of the books you see will still do the old thing, at least in introductory chemistry. And I don't bother reviewing organic books. I said, this is about all I can do with organic chemistry is make jokes about what they do. And when I went to school, it wasn't that much of a joke. I had to learn it anyhow. Okay, so coming back to this thing, that would, the double bond or the functional group is the first thing you would consider when you're numbering. So the functional group should always have the lower set of numbers. If it doesn't matter either way, in other words, if I put a methyl here, well, I guess, yeah, I have to number it this way, so the methyl has the lower. In other words, if the functional group doesn't have the difference, then the substituent would determine what you would do. So without this, I could number it this way, or I could number it this way, but once I put this in, I have to number it this way because both cases it's a 2-ene, but this is 2-methyl, and if I tried to number it this way, it'd make it 3-methyl, it would make it wrong. But I'm not done with this one. Remember I said there's no free rotation about the double bond.